Now that we know what Gaussian processes are, let's see how they can be applied to machine learning. So you have some points, x1, x2, so on, xn, and you know the values for them. Those are f of x1, f of x2, f of xn. And normally what you'd like to do is to predict the value of the function at new point x. For Gaussian process, we'll go in a bit different direction. That is, we'll try to predict the full posterior over the f of x given all our data points. So we'd like to estimate the probability of f of x, the prediction at new point, given all previous points. This will allow us to compute the mean, for example, and also to compute the confidence intervals at each point. This will allow us to estimate uncertainty of our predictions. So how do we predict this? Here we have our desired value, the probability of the prediction given our points. It equals to the ratio between the joint probability over all points, including the new one, over the joint probability over our data points. Those two are normals. The one in the numerator would be normal with mean 0 and the covariance matrix C tilde, and in the denominator we'll have the normal with mean 0 and covariance matrix C. So the covariance matrix C would have the following form. On the diagonal we'll have k of 0, this is the variance of the random process, and on the off-diagonal elements we'll have the covariance of the kernel function actually of the difference between the two corresponding points. The C tilde would look like this. It would be a matrix which has 4 blocks. The first block is k of 0, that is the covariance between f of x with itself. We'll have on the right lower part the covariance matrix C, corresponding to the covariance of the data points, and we'll also have the covariance between the new data point and the data points that we had before. So this would be the vector k. Its elements would be k of x, the new point, minus the old points x1. In the second position we'll have k of x minus x2, and so on. And so finally we'll have the normal distribution of f of x given mu as a mean and sigma squared as a variance. Do you remember why we have the normal distribution as the posterior? Well, actually this happens since the ratio between two Gaussians is also a Gaussian. We have parabola under the exponent. When we divide two Gaussians, we have the sum or the difference of two parabolas, and this is actually a parabola again. So the posterior again will be normal with given mean and the variance. One can derive the formulas for them, and those would look like follows. It would be k transpose C inverse f, where f is the vector of the values. It's like f of x1, f of x2, and so on. The variance would be k of 0, the initial variance, minus k transpose C inverse k. And these terms would show us how much the variance decreased after we observed the new points. So this is how the posterior distribution would look like. So notice here that the variance at the data points is 0. So since we observed their values, we can surely say that the value is just f of x1, for example. And as we move away from the points, the variance starts increasing, and if we are really far from the data points, the process would be simply stationary. So the mean would be 0 and the variance would be equal to the initial variance. This is k of 0. So we should actually pre-process our data to make it like stationary in the prior. That is, as we want our predictions to be stationary when we go away from the data points. So we would like to expect that the mean value is 0 and the variance would be k of 0. To make this true, we should remove the trend and seasonality, and also subtract mean and normalize. And so after training the Gaussian process, we'll have some function like this. You should also remember to invert all those transformations when you predict for the new point. That is, you have to denormalize, you have to add mean, add trends and seasonality, and output your prediction.